Welcome to MyProjectBazaar.com. Now we discuss about the product for single-ended 90 SRAM cell for near threshold voltage operation with enhanced read performance in 22 nanometer FinFET technology. Next, we see the abstract for the product. A low power circuit is an important issue in a portable and battery operant application. An attractive method to reduce the power consumption is supply voltage scaling. Recently, circuit designers have focused on near threshold and sub threshold digital circuit designs to reduce the power consumption. In this sub voltage threshold region, minimum energy can be achieved. However, the performance in this region is significantly degraded. On the other hand, balanced the near voltage threshold region. The near voltage threshold region is a critical issue mobile system on a chip. However, the increases in voltage threshold variation in the near voltage threshold region can be endanger the stability of the circuit operation. Static random access memory cells are typically designed causes a large mismatch between the paired transistor in the SRAM cells. Thus, the SRAM cell can be particularly vulnerable to the voltage threshold variation. In such cases, the read stability and the writability of SRAM cells will be significantly degraded, which in turn the limited of supply voltage scaling. To reduce the voltage threshold variations, alternative devices such as the fine-shaped field effect transistors are proposed. A field effect transistor reduces the random dop dopant fluctuations with the major contributions to the voltage threshold variation due to the undoped channel in provide better short channel control the planar bulk MOSFETs owing the 3D structures. Although near voltage threshold variation is an attractive method for energy and performance constrained applications, it suffers from the problem in terms of the circuit stability, particularly for static random access memory cells. This the brief process proposes the near voltage threshold 90 SRAM cell important in 22 nanometer FinFET technology. The read buffer of the real bit line and the improve the read performance using the one transistor read path. Energy and standby power are reduced by eliminating the sub voltage threshold leakage current in the read buffer. For the accurate sensing yield estimation, a new yield estimation method is also proposed. Next, we see the flow diagram for the product. Given a 2 input data bits for our overall SRAM memory architecture, this SRAM memory architecture consists of the 9 transistor based SRAM cell designs. These memory cell designs mainly focused by the layout based structure for using the microwind software. The 90 SRAM memory layout designed to be designed for our 2 inverter cross connection based structure and the memory writing process input control bits to be applied in our the SRAM cell. The writing process to be controlled in another on 2 transistor and the write and read the output data bits to be controlled by the another one transistor. So totally consider the 9 transistor based layout structure for our overall architecture design. This designs done to calculate the final simulation graph and the power analysis graph. The simulation and power analysis graph mainly based on our overall 90 SRAM layout based structure output operations. Then we go to the process for the 3D layout based structure designs. The 3D layout based structure designs to be updated for our overall simulation based output waveform for the required 9 transistor memory CMOS design working process. The 9 transistor to maintain the threshold voltage level and to stabilize the read and writing performance for our overall layout architecture designs. This layer consists of the metal based and the 2 metal and the poly structure based our overall architecture output design. This is our the final flow diagram for 90 memory CMOS design processing for layout structure architecture. Finally, we see the output for the product. This is our the final design for 90 SRAM layout architecture. These are the internal structures for the metal and metal 1 and metal 2 is the contact material and the polysilicon and contact material. This is the N diffusion and P diffusion and P mass contact and N mass contact architecture. These are the internal components for our overall architecture design. This is the inbuilt region context. These are the layer structure for our overall architecture. These are the 90 SRAM layout architecture. This architecture to apply the input for two input for the bit input and then inverting bit input, and then another one input for the writing enable conditions. Whenever the write is activate, write is set, the data storage to be activate, and whenever the write is not set, the data storage to be not enabled for the output. When the write is completed, the read operation to be set. Whenever the read to be set, what are the data to be stored in and to output to be displayed. The read operation is not set, the data to be 0. This is our the overall SRAM architecture for our 90 SRAM layout structure. This layout structure mainly used to control our overall architecture based process and final output designs for our overall SRAM layout architecture designs. This is our the final design. Then we go to the simulate our overall SRAM architecture results. This is our the final graph for our overall architecture process. This is our the structure designs, and these are the clocking for the read and writing control for our overall architecture. This is our the data input, and these are the writing control and the reading data bits. Whenever the data to be set, the clock to be activated and the writing control to be activated and the reading control to be activated, the data to be read. And the reading control and the writing control and the clock control to be not activated, the data not be write. So whenever the data to be present, it's a 0. Then the activation control, the data to be write. These are the overall simulation graph for our 90 SRAM layout architecture. This is our the layout based, our output based structure. This is our the overall power consumption for 0.709 milliwatts for our overall power consumption architecture. This is our the final simulation for our required 90 SRAM layout architecture design.